Okay, this is lesson 3.3a, and this is some data from GapFinder. This is income per person around the world, and then the life expectancy. I would think that the higher the income, the greater the life expectancy, but that doesn't always work like that. There are definitely a few outliers there. What I mean by outliers is they have a large residual there. There might even be an influential point or two out there. Wow, some people make a lot of money. Some countries, it's surprising. Those two influential points out there. Well, and their life expectancy is pretty good. Okay, so the color of each circle indicate the geographic region in which the country is located. Okay. So the bigger circles indicate a larger population. So you can see the United States is, relatively large, but there's some other large countries out there as well. It's definitely not linear, right? So the first thing you might notice, you go, well, it's not going to work, right? We're not going to be, we like to do linear regression, and this data is just not linear. However, we can straighten out the data. So this is almost like cheating, not really, but it's what we do in stats. We just go, well, could we make the data linear and then do linear regression? Because we really like linear regression. And we can. So if you take the log of income per person, I know that seems like a strange move, but if you take the log of the x values and plot those values, now you can see the data looks fairly linear. I think you would probably pass that test, that it would be linear. All we did was took the log of the x values. You might say, well, how do we know to do that? We might have been a trial and error kind of thing, but it's called transforming the data. Sometimes we don't know how to do that. Consider a power model. So today's lesson is about different kinds of power models that you can do, or even logarithm. Okay, so sometimes it is involved raising x to some power or y to some power, or conversely taking the square root or the cube root of x, or taking the cube root or the cube root of y, those kinds of things. So here's some data. You've been organizing a fishing tournament, looking for the heaviest type of fish, but fish evidently are hard to weigh, and so you find out it would be easier just to measure their length and then use a scatter plot to make an estimate of how much they weigh, and that would be easier for some reason to do this. So here's the data. Unfortunately, the data looks nonlinear. It looks kind of curved there. When you look at the graph, so you go, well, we're in APSTAT, we really want to do linear regression. Is there any way we can make that data linear? So we're talking about length and weight. Weight is kind of a three-dimensional kind of measurement there, where length is one-dimensional, where you're measuring one. So I'm wondering if we could do something to that weight variable there. And so they suggest, well, maybe you can make the length like cube it, and that might equal the three-dimensional weight. Okay, so we could have maybe cube rooted the weight, but we decided to cube the length, and that maybe makes sense. Okay, and again, this might be a trial and error thing. It's not like there's one right answer to make the data linear. There's other things we probably could have done to this to make it linear. But what they did is they cubed the length, and there's the data, and see because this transformation to form a linear regression. Okay, so they did the linear regression, so you have the data there. So what you would then do is go, okay, identify the equation. So the equation would be weight is if you look back at the figure, you can see that weight is the y variable there, and length is the x variable, or maybe I should say length is the explanatory, and weight is the response. In the chart, when you look at this data, sometimes I look at the first line there, which says regression analysis, weight versus length cubed. So that's saying the y variable is weight versus the x variable is length cubed. And so you would just set up your normal y equals a plus bx equation, but instead of y, we're plugging in predicted weight. Instead of x, or the explanatory, we're plugging in length to the third power. So you have to kind of add that little twist there. I think that's the real difference in today's lesson is you're going to have, either x or y can be modified, or maybe x and y are modified. You can actually do it that way as well. So then you're going to plug in your value that they ask about. So suppose it's 36 centimeters long. So you're going to plug it in, and it comes out. The predicted weight would be 688.9 grams, just using your calculator to type that in your calculator. So that one's pretty straightforward. As far as they did it for us, that was nice. So again, we're going to consider, so it should produce a scatter plot with linear form. So you can see that this scatter plot is somewhat linear, and so that's why that worked. Linear regression only works when it's linear. We could have done it this way. We could have taken the cube root of weight. I think there's some other ways. We could have used logarithms. We could have used another way as well. It's not like there's one right way to linearize data. You can do it many different ways sometimes. Okay, so this one, if we did it this way, so this is, and I think this is the tougher way of doing it. If you adjust y, you've got to do a little something on the back end here when you plug in and get this equation. So again, the equation, normally it's y hat equals a plus bx, but y hat is cube root of weight, x is length, and so you're going to write your equation here. So the equation would be the cube root of weight, predicted weight, is negative blah, 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 blah. So there's your equation from the data. Again, the thing in the data, if you're not used to this yet, where you've gotten used to this, when it says constant there, the number next to that, that's the y-intercept. That's that negative 0.02204. It says coefficient, the number below the constant is always the slope in both computer formats. So I always remember that. The number below the y-intercept, if you can find that, is always the slope. So the slope is 0.2466. And so it's always just nice to be able to identify that from, you get better at that after a while. This mini tab output from a computer, it becomes more normal. So now if we plug in 36 for the length, we've got to do an extra adjustment. So you get 8.856, but that's the cube root of weight, right? So you have to take that number and cube it to find the actual predicted weight. So there's an extra step. Whenever you adjust a y value, there's always going to be an extra step there. Okay, so working with a power model, you can transform data by, again, raising x to some power. You could put y to some root there, those kinds of things. What if you have no idea what value of p to use? Both variables should produce a linear. So that's actually like a backup plan. Well, maybe take the log of x and the log of y. So that actually happens where that'll kind of work. Take a log of both sides. This is the meaning behind that as to why it might work. But let's maybe try that. So let's see. So in the pre-examples, we use powers and roots, same example, same data. So this time, if you take the log of x and the log of y, that data looks somewhat linear as well. So there's not one way to linearize data, if that's such a word, it's linearize, but I think it might be. Okay, so if you did it this way, your equation would be, so the first question was, is it reasonable to use a power model to describe the relationship? So if you look at the residual plot over here to the right, that looks somewhat scattered. I don't love that there's a lot of clumping there, but there's no obvious curved pattern. So I would say that linear fit is a decent fit here. And so that's what you're looking for, is some scatter in there. Give the equation. So in this case, again, it's going to be the log of the y variable. And then the y-intercept, again, we get that from next to constant. There's the y-intercept. Always below that is the slope. And instead of x, we said the log of length, x, or log of x. So again, both of those are being put to a logarithm. So to get the answer, log of weight equals, once you plug in 36 there, you get 2.84. And now you have to be able to kind of change the form of this. Do you remember changing the form of this kind of equation? If you use logarithms, you actually have to know how to do logarithms to kind of undo it at the end. You can do the first part just fine, but the last step, it might be a little bit hard for you. So in this case, you would put this into exponential form. Remember, exponential form is a base to a power equals some number. So the base in this case is 3. That's the number down low. A logarithm is the exponent. The exponent's always on the other side of the logarithm. So x is the exponent, and 9 is the number over there. So You would rewrite that 3 to the x equals 9, 3 squared, of course, equals 9, and that's how you do that problem. So let's try to solve this problem. The problem was log of the predicted weight, I'm just going to put predicted W there, equals 2.8464. The understood base there is 10. I hope you remember that. When there's no base, it's understood to be 10, unless it's natural log, and then it's understood to be e. So we're going to put this in exponential form. So to do that, you're going to put the base, which is 10, down low. The exponent's always on the other side, so it's got to be this 2.8464. And then the W hat weight, predicted weight would be over there. And that's what they did. They didn't show all that work. But they basically said, okay, predicted weight is 10 to the 2.8464, and then they typed that in the calculator to get an answer of 702.1 grams. So it's a little tougher with that. The other way you could do this, I just thought about that. This is stats class. I mean, we don't have to actually do that much math, is you could type this. If you can get to this step, you could type that in your calculator and the solve command and solve it for W or X or whatever variable you use there, and that will solve it. And so the solve command is another way to go with this one, actually. So that could work. Let me just demonstrate that in case you're struggling with that one. Okay, so if you want to try that, we could go and try it. So menu 3 solve, and then we're to type in, I think it was log. So log is in blue, so control, there it is. Log base 10, I'm just going to leave that blank, of X, I guess we're going to say, equals 2.8464, comma the variable we're solving for, and it put 10 in there because it knew there was a 10 there, and the answer is 702.1. So it will do it that way as well. So I'm fine with that. If you can set it up and just use your calculator to solve it, that's not really a problem in stats class. Okay, here's a scatter plot of the data. This looks like a curve. It almost looks linear, but man, I think that's going to be curved there. So we might need to do something with this. So volume, radius is kind of a one-dimensional measurement, kind of like length. Volume is usually a cubed kind of measurement. So I'm thinking either cube or square the radius, or square root or cube the volume would probably work here if you wanted to think about it that way, to make that work. So what they did is they squared the radius, and just they kind of looked at it and go, okay, that looks pretty good. And so if you did that way, then you're going to write the equation as the predicted volume, and instead of radius, therefore X, you're putting radius squared because they squared the radius. And then the answer, you don't have to convert the answer when you don't adjust the Y value. So sometimes it's easier to adjust just the X value because you don't have to convert the answers. It's not as difficult. So if you can just adjust the X value, that's probably a hot tip that would actually help you, I think. Give the equation of the line. So in this case, it would be the volume, the predicted volume, and then the radius. This way, so they did it the square root of the predicted volume, right? Because this time they chose the tough root and they adjusted the Y value. Of course, if you do that, the last step, you're going to have to square both sides. So that's why that 5.12655 is being squared, because we had to solve for volume, not square root of volume there. So whenever you adjust Y, you've got to do an extra step there. Okay. Great. We had some good practice there. That is the end of our lesson for today.